All right. Hello, everybody. This lab recording is for the Monday lab group. Um, you guys would be a week behind if we didn't have this lab recording to give you a chance to make up this lab during the week. So before we get into the lab, which is about the general sense and special sense of hearing, I want to say a few words about the mechanics of the lab. In the orientation video, I didn't say a whole lot about it. It's a lot better to explain these things once we are about to start the lab. Maybe before we get into the topic itself today, I want to take you to a screen share and let's take a look at that lab schedule. You can access it from your class shell. Let me do the screen share. All right, so I hope you can see this. This is your lab schedule. We are meeting after Monday's lecture. The lecture ends at 12:15, so we have a 15-minute break. And then from 12:30 through the same Zoom ID and passcode, we start the lab. Again, here's the indication. I'm asking you to make up Monday's lab by watching this very recording. And here are the topics. So you see these weekly labs here listed, but we do see other things in these in this lab schedule as well. The first thing perhaps is that after the closing of the lab, a lab home assignment opens in Blackboard. This is a non-proctored graded assignment. This is the only assignment in this class where you have 2 chances to complete this. What exactly is a lab home assignment? So this is 15 questions. You have 20 minutes timing to answer these. And just like every or almost every question in lab-related assignments, these are fill-in-the-blank type. So you will have to type in your answer. Multiple choice, true or false questions will be very hard to find. You will see a few scattered here and there, but 99% of your questions in the lab will be fill-in-the-blank type. You must have the vocabulary to type in these answers. Requires a little different preparation from, let's say, preparing for a chapter quiz or lecture exam. So you have several days to do this. The lab home assignments are due midnight before the day of the next lab. So the due date for this first lab home assignment is Sunday, midnight, January 24th. And again, you have 2 chances to take a look at those 15 questions. Many students click into this lab home assignment, look around what the questions are, study and collect the answers, search for them, and when you click into this lab home assignment the second time, now you have a full set of answers to put in. My expectation is that all of you will be scoring very highly on this. It does take some preparation. The purpose of the lab home assignment is to encourage you to study lab material. This is true, especially in the virtual world. However, I hope you all listen to the orientation video. Remember that grading segment, a good chunk of your grade depends on your lab performance. You must make at least 65% in the lab-related assignments. So lab home assignments, you can make this very easy, a constant 100% achievement because you have 2 chances to look at this. Another thing that is different from lecture is quiz. So on Monday, January 25th, we start the lab with a quiz that we'll be doing through Zoom. So this will be a live quiz. And this is where we'll have the first chance to try that proctoring protocol you will enter the meeting through your phone, and the quiz will come to you through your laptop or desktop. This will be a really great way to test drive that proctoring protocol. So the topic of the quiz is everything that we covered in the previous lab. So exercise 23 and the hearing related lab information. And once this quiz is done, we'll talk about the correct answers on that quiz. So you receive an instant feedback. And then we move on to the next exercise. Next Monday, I'm sorry, on the Monday of the 25th, we have the olfaction, gustation, vision to close out the special senses. And then you see again a lab home assignment opens about that lab. And the following week, you have a quiz on the topic of now olfaction, gustation, and vision. So this will be a pattern throughout the lab. My hope is that this section can duplicate the very, very good results students achieving in AMP2 labs. So by the time it comes to the lab practical, everybody will be prepared. The practical questions will be very similar to what you see in the lab home assignments and in the lab quizzes. So there will be no mystery. What is the type, style, depth of the questions on the practical? And of course, you got a tremendous practice because on the lab practical, you will have to write in, guess what, fill in the blank type of answers. So this is the best way to prepare for the practical, work diligently on the lab home assignments, prepare for those quizzes, and you have a golden chance to do very well on the practical. So the question always comes up, okay, what to study from the lab? So to help with this, a couple of years ago, I started doing guided note-taking, which means handing you a note-taking guide. So let me exit from this screen share. And so for this lab and for all the labs that we will be doing together, it's really good to have this document. I'm holding in my hand a lab report on general sense and hearing. So this is the lab report, the guided note-taking document for this first lab. You find this lab report in a PDF form. If you go to your homepage in your class shell, not the lab shell, in the class shell, scroll down on the landing page and you'll see a folder that's titled Lab Reports and Supporting Info. Once you're in that folder, the very top file should be lab report on general senses and hearing. And please print it out. In order to facilitate, encourage you to work on this, I will be giving you 10 points for every lab that you are attending based on your Zoom signature. I'm not going to collect this lab report. I hope that you trust me. Maybe you can ask your peers, ask people who previously took AMP2 with me, and ask them, was that lab report useful for their preparation and achieving their grade goal? My guess is that in most cases, the answer will be yes. It's still a lot of work. This is not a magic bullet, but it's a pretty good tool to make sure that you achieve your grade goal and do sensational well in the lab portion of this class. So I have a set of PowerPoint slides, and sometime we go and visit the lab shell. We're going to do both of that today. At the end of the lab, I will attach that PowerPoint presentation next to the lab report in your class shell, and that will complete the set of materials that you will be using. So when you look at this lab report, and of course you can stop this recording and print this lab report What we'll be doing is starting with the first item here. I tend to go through all the points. There's plenty of room to take notes. This can be the most valuable document you create for yourself in your own handwriting, and write down what you believe is important, how it relates to the images that you will be seeing, where those images are coming from. You can record all that. And when it comes to prepare for a lab quiz, lab home assignment, but also for the practical, this lab report can be a document worth its weight in gold. So today's lab starts with general senses. If you listen to the lecture, and usually the lecture precedes the lab, so you might want to listen to that recorded lecture first. But let's say a few words about general senses. Sensory neurons are responsible for detecting changes in the environment. And many of those neurons send their nerve impulses to the consciously working part of the brain. When that nerve impulse arrives to the brain, we consciously sense that something changed in the environment. The general sense group of sensory neurons are scattered throughout the body. We'll see a brief look at a skin model. We'll be looking at a table from a lab manual. So your lab manual will also be pretty useful for this lab, not only for this purpose, but others as well. So we are starting our discussion, general sense, sensory neurons scattered throughout the body, and they are detecting changes in the environment. So what can we possibly say about these general sense neurons and the general sense themselves in the lab? We can look at them under the microscope. We'll be looking at them on a skin model, and we'll be looking at a summary table with all their properties. So without any further ado, let's take a look at the first item on this lab report. And this first item reads, using the skin model, name a general sense receptor that is stimulated by touch and structurally classified as free nerve ending. All right, well, that's the way to get started. Not only getting our feet wet, doing a somersault into the water. So let's take this one step at a time. Skin model. So to show you the skin model, this is in your lab shell, but I'm going to go to this screen share. This is the first slide in a set of PowerPoints for today's lab. And again, I'll be attaching this. So you'll find this in the lab shell as well. So here's our skin model. And so you see several general sense receptors labeled here. Meissner corpuscle, just a free nerve ending without any function here. We have Pacini corpuscles, and we have hair root plexus. So the question here in front of us, name a general sense receptor that is stimulated by touch and structurally classified as free nerve ending. Well, where in the world would we get that information from? Structural classification in what is the stimulus that acts on these general sense receptors. So here comes the importance of the lab manual. And let me bring mine over here. In exercise 23, there is a table 23.1. The page number differs dependent on which version of the lab manual you have, but you'll find it table by this number, table 23.1. In this table, you see several columns. The first column is a name of the receptors. And when you look at the skin model, you'll see that, wow, there's Meissner corpuscle, Pacini corpuscle, hair root plexus. These are the first three receptors. But then you see a bunch more that we don't see on a skin model. I'll come back to that. Our first question is related to what we can see actually on a model. So let's take a look at the second column. This is the location. And here you see the Meissner corpuscle tucked into the dermal papilla. You see the Pacini corpuscle under more subcutaneous tissue. And you see the hair root plexus right around the hair follicles. The third column in this table is the structure. General sense receptors can be of two kinds, either free nerve ending, and with a free nerve ending on a model, you just see yellow lines. So here's another free nerve ending. This is how it looks. And then we have the encapsulated nerve ending. Encapsulated nerve ending, there's always a capsule. A capsule is an oval structure. Look at the Meissner corpuscle. Here's a capsule of the Meissner corpuscle. Here's a capsule of the Pacini corpuscle. And you see more Pacini corpuscles here. There's one other Meissner corpuscle peeking out here to the left. These are both encapsulated nerve endings. So this is the structural classification. And the fourth column in this table, you see the stimulus. The stimulus is the change in the environment. When you look at Meissner corpuscles, they detect touch and pressure stimulus. Hair root plexus detects touch of hair. And the Pacini corpuscles detects touch and pressure. So when we put all this together and come back to this question, name the general sense receptor that is on the skin model, stimulated by touch. Well, all three of them are stimulated by touch, and structurally classified as a free nerve ending. So that brings us to the hair root plexus. This is the only one that is a free nerve ending and classified as a touch receptor. Again, this free nerve ending, we don't know what this is. We don't know what stimulus this detects. When you look at that free nerve ending and you look into this table, you'll see that several receptors have this free nerve ending. So this one on the skin model could be detecting cold or warm. This could be a nociceptor or pain receptor. So there are a number of possibilities. We don't know what it is. Model makers just don't tell us what it is. So the first question here in the lab report, we ended up with a conclusion of hair root plexus. Please take a note of this table. We'll keep going back to it, and that this skin model is on the lab PowerPoint that will be attached next to your lab report, but it is also in the lab shell as well. Well, question number 2 here in the lab report. From a table in your lab manual, name 2 typical anatomical locations for proprioceptors. Okay, in lecture, we did look at very briefly proprioceptors. These are sensory receptors that detect the position of the body. So in the table, you have to go all the way to muscle spindle and tendon organ. Now the names don't have this word proprioceptor, but take a look at what they do. Muscle spindles respond to changes in muscle length. So if you're moving a limb and muscles are contracting, body position changes, muscle spindles detect that. So they are proprioceptors. Tendon organs. Take a look at the stimulus, respond to changes in joint position and movement. So these two are classical proprioceptors. For our lab report, we also have here name two typical anatomical locations. Well, the muscle spindles are in skeletal muscle. The tendon organs are in tendons of skeletal muscle. So the name of the proprioceptor tells you the location as well. I'm going to stop sharing here for a minute and come back to this table. When you look at this table, you'll see other receptors here. Type 2 cutaneous mechanoreceptors, cold receptors, warm receptors, nociceptors. These are all general sense receptors. When you look at their location, most of the times you see them in the skin. Pain receptor or nociceptors are in every tissue, well, almost every. The brain, for example, has no pain receptors, the nervous tissue, but many other parts of the body does have it. Here is the reflection on what general sense receptor means. These sensory neurons are scattered throughout the entire body. Skin is the biggest organ, but there are other places such as skeletal muscles, tendons. Again, there's a scattered gross anatomical nature to these general sense receptors. In a live lab, in a face-to-face lab, we would follow this up with the most fun experiment. On the first day of the lab, you get to poke your neighbor with an instrument to take measurements. We're going to skip that. So your lab report is saying, name the experiment that measured sensory receptor density. Please scratch that. We're going to leave that totally off our radar screen. Question number 4, or point number 4 in the lab report. Name the sensory receptor stimulated in the experiment to study adaptation. Let me go back to let's see, we can go back here. And I'm going to go out of sequence in this presentation. So here is the general idea of adaptation, because this is important to talk about. This is something we mentioned in lecture as well. This is an inherent property of all sensory receptors, that when we have constant stimulation of a receptor, that receptor will create fewer and fewer nerve impulses. Why do we care? Or how do we notice it? How do we know this? We notice it because fewer nerve impulses mean that we are perceiving low intensity stimulus. So how can we possibly test this or demonstrate it? And this is what this lab experiment about. I just have an image here. And in your lab manual, the experiment is described. So let's say a few words about this adaptation experiment. First, the adaptation is testing the warm receptors of the body. Please write this down. Name the sensory receptor in point number 4. We are testing the warm receptors. How do we do that? You see the end of the experiment here. Let me go back to step 1. So we put warm water into this bowl, and the experimental subject, usually you, the students, put one hand first into this bowl. The sensation that is created by this action is that the water is warm. Now, adaptation should make the warm receptors in this hand create fewer and fewer nerve impulses. And this hand would keep telling us that the water is getting lukewarm. To get an absolute lock on this weakening warm sensation from the adapted hand, we for a second immerse the second hand in the same water. And what most students detect in this experiment, that the unadapted warm receptors on this newly immersed hand will give us a higher temperature reading, and you will have the weird perception, one hand giving us a lukewarm, while the other hand giving us a much warmer sensation. So your two hands would be detecting two different temperatures. And that's because we adapted the warm receptors on this hand by immersing this hand for a minute in warm water and giving it time to adapt. So this is the adaptation process. Your lab report comes back to this on point number 5. During the process of sensory adaptation, the sensory receptor creates what nerve impulses? Well, let's see. The answer is right here. The sensory receptor will create fewer nerve impulses. And again, as a consequence of that, we detect this as a low intensity stimulus. In the case of the warm receptors, it would give us the lukewarm feeling. So this is the experiment for adaptation. We mentioned this in lecture. All general and special sense receptors adapt. Some of them are slower, some of them are faster. The thermoreceptors, cold and warm receptors, adapt faster. So this was a great experimental topic. Again, we have been talking about an experiment where we adapted warm receptors on one hand and detected that decreased sensitivity by immersing the other hand right next to the first hand and detecting a temperature difference. And this is a point where I'm going to show you one more document. Let me see if I can find it here. Give me a second. All right. I thought I had this here, but I may have to look for this. All right, well, this document that I was talking about is the lab practical study guide. I want to put this on a screen, but you can access this from your class shell. On the first page of the lab practical study guide for practical 1 would explain that we were supposed to be looking at all these topics that we so far have looked at. There's one item there. This is not covered in the lab report. This is more for general discussion. And the topic is, last topic on that practical study guide is the topic of referred pain. Now, we no longer carry out an experiment in the lab. We mentioned this briefly in that first part of the lecture. A referred pain is a type of sensation where pain receptors are not signaling actually any kind of pain. So how is this possible that we have a pain sensation when we don't have any tissue damage? The opinions diverge how this is created. All we are going to do here is list an example or two. One example of a typical referred pain is the pain of the heart attack. During heart attack, most people feel excruciating pain in the left shoulder area, maybe the upper arm. And this pain sensation feels like that something is damaging tissues in those areas of the body, but there's no physical damage. It's the heart that is getting damaged. It's heart that is undergoing this stress of heart attack. So in this case, we can say that our brain is interpreting a pain sensation when there is actually no pain stimulation. So this is the referred pain. Pain receptors are not signaling, they are not creating nerve impulses, yet our brain is indicating that pain is happening at a particular body part. Another example of referred pain is an experiment where you can take your elbow and stick it into ice water for 2-3 minutes. And that's supposed to create a tingling feeling in your pinky finger and part of your ring finger. This is the same effect as hitting your funny bone. So hitting your funny bone is damaging your ulnar nerve, which is running into this groove of the trochlea. And that is an example of referred pain because what you are sensing is pain, tingling feeling in the pinky finger and in the ring finger, not at the point of the elbow where you hit it or where you stuck it into ice water. So again, there's a mismatch between what our brain is telling us and what the pain receptors are doing. Some of the referred pain is created by nerve impulses put on an unusual track, unusual path of neurons that reach our brain in an inappropriate place. So this is these were two examples of referred pain. And that's all we have in the lab with regards to the general senses. So please keep an eye on that table 23.1. And also you'll be looking at the lab PowerPoint. In this table, it's good to match a particular receptor name with its stimulus, location, structural classification. We have had the model, and let me go back to the screen share here. So these sensory receptors, go back here. You're supposed to recognize these receptors from a skin model and relate them to stimulus, structural classification, location. And then we do have two microscope slides. The Pacini corpuscles show up in cross-section as two lumps. Here's one, here's the other one. You are supposed to recognize these Pacini corpuscles from this microscope slide. And the only other microscope slide that we have about general senses is the Meissner corpuscles. You see both of these Pacini and Meissner corpuscles on the skin model. This is what they look like in real life. Here's the dermal papilla, and inside the dermal papilla, filling it out completely, is this barrel-shaped Meissner corpuscle. You can see this a little better here. Unfortunately, these structures shrivel a lot when the skin is prepared for microscope slide. I hope you all recognize or find this familiar. So right here, we have the epidermis with the stratum corneum, stratum lucidum, the dark layer is a stratum granulosum, and down here is stratum spinosum. So in that stratum spinosum, there are these invaginations, dermal papillae, Meissner corpuscles sit right there. And down at the bottom here, there's dermis. So just to give you some orientation on this slide about Meissner corpuscle. So recognition of these receptors from model, from these two microscope slides will be important, and being able to relate all that to information in the table 23.1. As we're going along, you may have a bunch of questions. Please write them down for yourself and send me a message through your class shell. I'll be happy to answer these. Again, your quiz on this will not happen till January 25th. Your lab home assignment will be open for several days. So there's no imminent rush, but if you have questions, please send them my way. And so with the adaptation, we have closed the general sense portion of the lab. The next portion of the lab is about a number of special senses. So for the special senses, the major gross anatomical difference is that the sensory receptors are no longer scattered throughout the body. Let me move to the next slide here. Excuse me. So here's a model of our hearing apparatus. The receptors for our special sense of hearing are mechanoreceptors. They have to be physically deformed. So when you look at this entire body, our receptors for hearing are located only in this snail-shaped structure we'll be calling the cochlea. So this is in tremendous contrast to the Meissner corpuscles, Pacini corpuscles that are scattered throughout the body. So special sense of hearing is called special sense because the receptors are exclusively located in this area of the body, not here, not in the adipose tissue, not in the skin. All of them are bottled up in the cochlea. And if we lose this portion of the body to injury or viral infection, we lose our hearing. So this is the best illustration of the contrast between general sense and special sense receptors. So the first special sense we will be dealing with is hearing. In your lab report, point number 6 is about the movement of pressure waves, sound waves. What do pressure waves have to do with special sense of hearing? In the cochlea, those hearing receptors will have to be physically pushed to create a nerve impulse. Where is that force going to come from? Well, that force originates from sound waves in the air. It takes a long journey to go from air all the way deep into the temporal bone to the receptors in the cochlea. So we'll be talking about this path of transmission of pressure waves. Let's start at the beginning. What is sound? What is that we detect with the special sense of hearing? Sound is nothing else but vibration, pressure waves in the air. So To sketch out our hearing apparatus, we divide the hearing apparatus into 3 regions. And your lab report shows it external, middle, and inner ear within point number 6. So external ear, you see all the structures here labeled on this model, whether it's the auricle or helix or lobule. This is the visible portion of our hearing apparatus. Then we have the external ear canal, and the external ear region ends with the eardrum or tympanic membrane. Then we have the middle ear, and then we have the inner ear. The receptors are in the inner ear, and the inner ear is totally buried inside a skull bone, the temporal bone. So it takes quite a bit of effort to move pressure waves from the external ear all the way to the inner ear. Let's take a look at the structures that transmit pressure waves. The first part of the external ear are just funneling the pressure waves. The first structure that will actually be transmitting, passing on the pressure waves is the eardrum. Eardrum is the first structure that starts moving when the pressure waves hit the eardrum, and a movement, the vibration of the eardrum, is the first sign that part of our hearing apparatus is copying the pressure waves and transmitting onto other structures. So in the external ear, please write down in your lab report, eardrum or tympanic membrane. This is the only structure that actually vibrates, moves, resonates, and therefore is ready to pass on this pressure wave to other structures. The set of structures in the middle ear is not quite visible here. I do have a table about this. So in the middle ear, we have a series of auditory ossicles. So in the middle ear, we have the hammer, the anvil, and the stirrup. You can use the Latin names if you prefer. So how can these auditory ossicles transfer pressure waves? Well, we already moving, vibrating the eardrum. The hammer is glued to the eardrum itself. So when the eardrum vibrates, the hammer vibrates too. So now the hammer is copying those pressure waves. The hammer is contacting the anvil. So the hammer passes the vibrations onto the anvil ossicle, and then the anvil passes it up to the stirrup. So we have 3 auditory ossicles vibrating. What's the big point? The big point is right here that the stirrup is passing on these pressure waves to the inner ear. So we managed using 3 auditory ossicles to move pressure waves through the middle ear. Now the middle ear is filled with air, and any liquid accumulating here is drained by the auditory tube. In the respiratory system, we'll see that the auditory tube comes into our nasal pharynx, and that's where all the secretions are drained from middle ear. So both the external ear and the middle ear has air filling to it. In the inner ear, let's complete this number 6. In the inner ear, the structure that will be transmitting pressure waves is the cochlea. We'll say quite a few words about the cochlea. For now, let's just put this there. In the inner ear, cochlea is transmitting the pressure waves. The inner ear, including the cochlea, is filled with a liquid, so it has a very different nature. Again, middle ear and external ear has air filling to it. Number 7 in the lab report is what is causing hearing loss during middle ear infection? During middle ear infection, the growth of bacteria create a layer of mucus. Inflammation creates fluid outflow from the surrounding structures. And so the middle ear is accumulating fluids. In some kids, the auditory tube is so narrow that the fluids don't drain away. Bacteria keep on growing, causing a worse and worse inflammation here in the middle ear. Why is there hearing loss as a consequence of middle ear infection? Well, that is because the auditory ossicles now have to vibrate in a liquid environment, and that liquid dampens, slows the vibration of the auditory ossicles. Slow vibration means very low level, very weak sound. So hearing loss is the result of the slowing down of the auditory ossicles in the middle ear. The rest of this lab is now moving into the inner ear segment. So you see it's circled here. I believe we have a much nicer view of the inner ear. Here we go. When we take the inner ear out of that model, this is, I think, the best angle to show all the parts. So the inner ear has this snail-shaped structure, the cochlea. On the other end of the inner ear, we see these arching, almost pretzel-shaped structures. These are the semicircular canals. And in between the semicircular canals and the cochlea, here is this potato-shaped structure with 2 bumps. This area is called the vestibule. So the inner ear has 3 parts: cochlea, vestibule, and semicircular canals. What we're going to see at the very end of the lab, that there are sensory receptors in the vestibule, in the ampulla portion of the semicircular canals, and in the cochlea. Interestingly, our hearing depends on the sensory receptors in the cochlea, receptors in the ampulla, and in the vestibule serve other special senses. We will be mentioning them in this very last closing table in this lab. There's an additional structure here, very bright yellow. This is the vestibulocochlear nerve, cranial nerve 8. Our special sense of hearing depends on this cranial nerve because nerve impulses created here in the cochlea travel to the brain through cranial nerve 8. And so this is a this is the only cranial nerve that carries hearing-related nerve impulses. Damage to the cranial nerve 8 would damage our hearing because nerve impulses would not have an efficient way to travel to the brain. So this is the general look at the inner ear. So let's raise our focus to the cochlea itself, because we are concerned primarily with the special sense of hearing. So we saw the stirrup tapping those pressure waves into the inner ear, and those pressure waves will travel to the cochlea. Here's a cross-section of the cochlea, and you see that inside the cochlea there are 3 chambers. This green backing on this model shows you the 3 chambers. So point number 8 on this lab report, name the 3 chambers within the cochlea. Please write down scala vestibuli, cochlear duct and scala tympani. The word in parenthesis is the type of liquid that fills out. So scala vestibuli is not the same as perilymph. Perilymph is the fluid that fills out the scala vestibuli and also the scala tympani. So as opposed to the middle ear and the external ear, the inner ear is filled with fluid completely. Now the filling of the cochlear duct is quite different. This is called the endolymph. In lecture, we'll take a look at the transduction process and how the special composition of the endolymph, the high potassium content, turns out to be so essential for the working of our hearing apparatus. So here are the three chambers. The chambers are separated from each other with thin, stretchable membranes. Let's take a look at those. Between the scala vestibuli and the cochlear duct, we have the vestibular membrane. Between the scala tympani and the cochlear duct, we have the basilar membrane. Both of them are thin, stretchy set of structures. The pressure waves are tapped into the liquid of the scala vestibuli. Pressure waves are rushing through this chamber and exiting the cochlea through the scala tympani. So the scala tympani leads the pressure waves out of the cochlea. To create hearing-related nerve impulses, we need the structures inside the cochlear duct. So point number 9 in your lab report is asking which chamber contains the hair cell receptors for hearing. Name the specialized fluid in this chamber, where we already named the specialized fluid, endolymph. And the cochlear duct has the hair cell receptors. More specifically, the hair cell receptors are located in this bump, in this mound of tissue. This is called the organ of Corti. And when we look at the microscope slide, we'll see a little better labeling of that. The labeling is not here, but you can see the hair cells are all in this area. So how is this, how are these hair cells possibly serve as receptors? As I mentioned, the cells need to be deformed physically. In lecture, we'll see a really good animation of this. Here, all I want to just say is that as the pressure waves are rushing through the scala vestibuli and scala tympani, the two membranes start stretching and bending and moving. The organ of Corti is start to move up and down, jiggle, follow the movement of the basilar membrane. The tectorial membrane is staying unmoved, and the hair cells will be pushed into the tectorial membrane. You can see the hair portion of the hair cells right here. So the hair portion of the organ of Corti and the hair cells will be pushed into the tectorial membrane, and that bending, that deformation will lead to the nerve impulses that we interpret as hearing. So these are the structures inside the cochlea. I'm going to go to the lab shell and find the microscope slide corresponding to this very same cross-section of the cochlea. So let's go to the lab shell. And actually, I have to go a different way here. So hang in there. We are in the class shell here. I'm going to go to the lab shell. And of course, in a lab shell, where would you go? Lab materials. Microscope slides for a practical one. You have seen the Meissner and Pacini corpuscle. Let's take a look at the cochlea slide. So here's the cross section of the cochlea. We have our chamber scala vestibuli, cochlear duct, and the scala tympani. We have the thin vestibular membrane. You can see how extremely thin this is. We have yet another thin basilar membrane. Here, the organ of Corti, the location of the hair cells is a little better visible here. So what you see in the microscope slide duplicates very, very nicely with what you saw on the model. And just to explain this once again, when pressure waves rush through the scala vestibuli, the scala tympani, vestibular membrane and basilar membrane start to move, and the organ of Corti will jiggle up and down, and the hair cells will be pushed into the tectorial membrane here. And that deformation of the hair cells will lead to the nerve impulses. Again, in lecture, we'll get into this a little deeper here. Structures connected with basic function is the most important aspect here. So once we created nerve impulses, we are in business because we are supplying our brain, where the target is the temporal lobe. We are supplying that portion of our brain with nerve impulses, and now our brain can provide a conscious awareness to us, which we call hearing. The next point in our lab report is about hearing tests. I'm going to go back to the lab shell here, and I'm going to take you to a table. This table is in your lab manual as well, but let's go through to the bottom of the lab shell. So what you're seeing right now is coming from a lab shell, and I'm going to scroll all the way down. So this is a table I was talking about. This describes the Rini and Weber tests. These tests use tuning forks. Obviously, these tests were designed long before the appearance of electricity or electric testing apparatus. So imagine in the early 1800s or the 1700s, somebody's complaining about potential hearing loss. How would you determine which ear might use some kind of a hearing aid? So, or just to document this hearing loss, Weber designed a test where you strike a tuning fork, put the tuning fork to the middle of the skull, like the top of the head, and lo and behold, this would be so cool to do this in the lab because it's hard to believe that putting something vibrating on the top of your head will create a perception of the sound. So the interpretations are here. You don't need to know this, but if you detect a difference of this sound in the two hearing apparatuses, left and right, you may have hearing loss in one ear versus the other. To take a look at a single hearing apparatus and decide whether is this conduction deafness or nerve deafness, this is where the Rini test comes in. So the conduction deafness is damage to structures in the external ear or middle ear. nerve deafness would be damage to the structures in the inner ear. How can you possibly decide between the two? So the Rini test, and this is the best test to identify conduction deafness in one ear, because the Rini test is testing one hearing apparatus at a time. So you are using a tuning fork, you strike the tuning fork and put the stem of the tuning fork right behind your ear. Right behind your ear is that tough bone, is the temporal bone. And just by shaking the temporal bone through that vibration, a sound might be created. If there's no sound when you touch the tuning fork to the bone, the most frequent interpretation is that that is nerve deafness. So in that case, a hearing aid would not help much. Conduction deafness may make this person totally deaf, but if the hearing tests indicate no sound detection, then and in addition to potential conduction deafness, there's a nerve deafness issue as well. Of course, nowadays, the Rini tests are done electronically. A tuning fork is just a fun way to test this. So what is there to remember about Rini and Weber test? And you might want to write this down. It's important to remember that these two tests are carried out by a tuning fork, and that in the Weber test, the tuning fork is placed on the top of the head. And in the Rini test, the tuning fork is placed right on the temporal bone behind your ear. And Rini test, again, is the more specific test. It can test one hearing apparatus at a time. And so this is all we wanted to say about the special sense of hearing. Excuse me. I'm going to go back to a screen share, which takes us back to this lab PowerPoints. Let me see. I think I just found it. And so, oops, sorry. So when you take a look at the inner ear, and here are three gross anatomical structures: the cochlea, vestibule, semicircular canals. We pointed those out on the model. What is the importance of each of these? Well, we dug deep into the cochlea. We found the organ of Corti, which is the microscopic site for the receptors. And these receptors in the organ of Corti giving us the special sense of hearing. What about the vestibule and semicircular canals? They do have receptors, similar mechanoreceptors. They have to bend. How they bend is done very differently. In lecture, we're going to explore that. Here in the lab, all we want to do is establish a relationship between the vestibule and its role in a special sense, and the semicircular canals and their role in a special sense. So let's go to the vestibule. So on the model, you saw two small bumps right next to the cochlea. And so inside those small bumps of the vestibule, we have patches of receptors, and those patches are called macula. So macula is the microscopic site for receptors in the vestibule. Macula receptors give us a very different special sense: static equilibrium. What is this good for? This is sometimes called a proprioceptor, the receptors in the macula, because we are receiving information about the position of the head in three-dimensional space. So let's say you move your chin all the way to your chest. You bend your head forward. The receptors in the macula detect that and communicate that to the brain. Same way, if you bend your head sideways, left or right, the receptors in the macula will inform our brain that our head is being bent or positioned away from a normal position. So this is the special sense called static equilibrium. In the semicircular canals, at the ampulla portion of the semicircular canals, we have cone-shaped structures. Again, neither the macula nor the crista are visible on this model. So this is why we describe that here in a table. So the crista is the location for the receptors. The crista receptors will be moved by flow of liquid inside the semicircular canals. And when that happens, we are receiving information about another special sense, dynamic equilibrium. So what could move liquid through the ampulla? I'm going to go back here for a minute to the inner ear. So take a look at the semicircular canals. Of course, they are filled with liquid, just like the vestibule and the cochlea. So when our head and our entire body is spinning, fluid will be moving from one canal to another, and they move through the ampulla. So if we move our head very quickly, fluid will be moved from one canal to the other, streaming occurs, and that streaming of the fluid will bend the crista, that cone-shaped structures inside the ampulla. This rapid movement occurs, rapid movement of the fluid here happens when our body is spinning or when our body is accelerating or decelerating. So if you are on a roller coaster, when it accelerates, this special sense allows you to feel that. Isn't that great? Well, it also helps, of course, maintaining proper body position. So inside the ampulla is where the crista ampullaris is located. And again, dynamic equilibrium allows us to detect the spinning or slowing down, speeding up of our entire body. We'll say a lot more about this in lecture, but static equilibrium, dynamic equilibrium sends a lot of nerve impulses to a part of the brain called the cerebellum. The cerebellum is the big coordinator of body position and skeletal muscle movement. So knowing what our body does in three-dimensional space, whether it's movement of the head or spinning of the body, helps a lot our cerebellum part of the brain to figure out how to counter that, what to do with that changes in body position. And the last thing I want to mention here, we saw this structure on the model, but nerve impulses for all three special senses are moved through cranial nerve 8. We'll be seeing a number of cranial nerves in AMP2. The official mention, and that's what I keep on these slides, lab slides and lecture slides, is the Roman numerals. So cranial nerve 8 looks like this in Roman numerals. So we have seen this on the model again. And so this table answers all the questions for the last point in our lab report, number 11, named the gross anatomical and microscopic location for hair cells or hearing, dynamic and static equilibrium. This table in this presentation has all the information about that. So what I'm going to do is stop sharing here. In a regular lab, we would take breaks. You're welcome to do this, of course, in this recording anytime. But this is the end of our first lab. And again, if you have any questions, please don't hesitate to ask. The PowerPoint will be attached next to your lab report, and the recording itself you will find in a narrated labs folder on your landing page. So I'm going to close this lab and again, just want to encourage you, if you have any questions, please don't hesitate to ask. On Wednesday during lecture is the first time when we actually meet. Please don't hesitate to bring your questions there too. I may say a few words about this lab on Wednesday as well.